Okay, this is the introduction, the very beginning introduction to why reactions happen, just to get a basic understanding of why chemical processes occur. What you need to understand first is that this is based on a theory, and theories are the best explanations for what we have, that reactant particles must be traveling fast enough to form an activated complex, which would bring the atoms close enough for an actual reaction to occur. In this particular case, hydrogen and oxygen, you can put them in a container and not have any water being produced. But if you start to accelerate these, if you start to heat these up, eventually you will get some hydrogens and oxygens that crash to form an activated complex, and you end up having a reaction occur where hydrogen and water are now, or hydrogen and oxygen are now combined chemically. But in order for that to happen, they had to be hitting each other with a fast enough speed in order to make the activated complex and have the reaction occur. The activation energy is the minimum amount of energy for colliding particles to actually make this activated complex. If we didn't have that activation energy, the atoms or the molecules will not react. We'll also see a little bit later on reversible reactions where the products such as hydrogen and oxygen can be formed from decomposing water molecules. And that does actually happen in a lot of cases. Pretty much all reactions do have a little bit of a backward end slant to them. Although most reactions will proceed from what we call reactants like hydrogen and oxygen into products like water. These are some energy diagrams to give us an idea of why reactions, or how reactions happen. Carbon monoxide and nitrogen dioxide need to be traveling with sufficient energy, and you have to boost them to form this activated complex. That energy required to form the activated complex is called the activation energy. Once you cross that hump and you've given it the sufficient activation energy, then in this case the products will release energy, and the products end up being a lower energy than the reactants. This is generally what the universe prefers. Really think of the activation energy. You have oxygen all around us. We have we have wood sitting there dry, but you don't see the wood spontaneously catching on fire. However, if you provide energy with a match, that is usually generally enough to get the wood starting to burn. You have to add a little bit of energy to get those molecules moving fast enough so that when they collide, they will actually react. And what the universe generally prefers, what molecules generally prefer, is that higher energy molecules release energy and become lower energy molecules. Now, we do have some cases where your lower energy molecules can be boosted up to form an activated complex, and the products will actually have more energy than the original reactants. This is not nearly as common. It does happen sometimes. Why that happens, we'll talk about in the next stage. But the activation energy is the energy required from the base state of these molecules, base state in both of these cases, to get enough energy so that they can form an activated complex, and then in one case release a tremendous amount of energy and become lower energy molecules, or absorb energy and become higher energy molecules. This is the reverse reaction. This is the reverse reaction of this process. And in the overall reaction, if I did carbon monoxide plus nitrogen dioxide, I would release energy, my delta H, which we've talked about before as a negative value. If I take carbon dioxide and nitrogen monoxide and combine them, and I can get them boosted enough that they form an activated complex to turn into carbon monoxide and nitrogen dioxide, that would be a positive delta H value because energy is absorbed. What you need to know about entropy and enthalpy. Enthalpy, as we've talked about before, enthalpy is heat. Generally, reactions, molecules like to go from a higher energy state to a lower energy state. They like to release energy. Most reactions are endothermic. That's not all reactions, however, because we have another component of energy, which we call entropy, which is the energy of disorder. If you think about the ability to do work, which would be able to do more work? If I had a piston that had some liquid water in the bottom, or that I had with a very hot steam. Hot steam has a much higher entropy and is able to release that energy as the energy of disorder. That's a component of the overall energy of the reaction. A couple of other definitions we need to know here. Chemical reactions can be spontaneous. So these are the ones the universe will allow. There's no real barriers to preventing spontaneous reactions to happen as long as they're provided with sufficient activation energy. Non-spontaneous reactions require quite a bit of intervention in order to proceed. In any spontaneous reaction, we have a term called delta G, which is a combination of heat and entropy. That overall value has to be negative. So therefore, I may have a situation where I'm absorbing some heat, but I'm also increasing entropy substantially. If I'm doing that, even though I'm absorbing heat, and molecules don't generally like to have more energy as products than the reactants, it can happen provided that I produce a great deal of entropy. That would mean my overall change in free energy, this is called Gibbs free energy, delta G, is a negative value, which means energy is released by the system. Every system above absolute zero has some internal energy. At absolute zero, systems do not have any energy because there is no molecular motion. There's no motion period of any molecules. Therefore, it is zero energy in that case. And why is this important? Because we can possibly use this energy, whether from heat or from entropy, or both, in order to do work. And that's why we have such a need for chemistry and an understanding for chemistry. That's how cars, that's how planes, that's how we make power, that's how we do lots of things that we need in everyday modern life. Reactions occur, again, due to the laws of thermodynamics. Now, these are the laws. They don't have any explanation behind them. We actually don't have great explanations for some of these. They're kind of mysteries still. If you want to win a Nobel Prize, this is in physics, this is a place to explore. So, what you need to know about thermodynamics. Energy is conserved. Energy cannot be created or destroyed in an isolated system. It can transfer from one form to another. Light can change to heat. Chemical can change to heat. Chemical can change to light. So different kinds of energy cannot be created or destroyed, but they can change form. Entropy of isolated systems. The second law of thermodynamics says that entropy will increase. Any chance it has, entropy will increase. Very rarely would you ever have a system that loses energy. And actually, if you do see isolated systems losing entropy and becoming more organized, then something is very odd and needs to be rechecked. If we go to absolute zero, entropy will decline. If you add heat to any system, entropy will increase. You go from solid ice, which is not, the molecules are not moving beyond vibrating, to a liquid water where the molecules are free to move around, to a gas where the gas particles move completely randomly. As you add energy, you increase entropy. As you decrease energy, you will decrease entropy until you get to absolute zero, when everything freezes, everything is solid. Even helium, which will freeze at 1 degree Kelvin, will liquefy at 4 degrees Kelvin, and at absolute zero, there is no disorder, there's no movement, period. That's just more of a physics thing you need to worry about, not really that concerned that you state the laws of thermodynamics, but understand that reactions will occur if they release heat increase entropy, or both. If they decrease entropy and they decrease heat, they're going to be non-spontaneous reactions. Spontaneous reactions need to have an overall release of energy and or entropy. This is a very exothermic reaction. Just to get an idea of the entropy going around, this is a solid, this is a molecule, this is a compound, crystalline compound. This is a gas, lots of entropy. This is a gas, lots of entropy. If this is a gas, even more entropy, or a liquid, a little bit less entropy, but still has more entropy than a solid. The entropy values per mole are given here. As with any energy, it's determined, or it's given in joules, and this is per degree Kelvin. So as we increase temperature, we would increase the entropy overall. I didn't get the sum values in here, but if I did my overall change in entropy for a reaction, this is my overall change in entropy for a reaction, I would do the sum of the products times their mole values minus the sum of the reactants times their mole values. What would that actually look like? Well, in this particular case, I have my products, which are carbon dioxide, 6 carbon dioxide plus 6 water, and I would subtract from that my entropy of glucose and my entropy of oxygen. What I find out is that there would be an overall gain in entropy if this reaction were to proceed. So the universe likes this. You're increasing entropy because you're breaking down glucose into oxygen. Glucose and oxygen, you're breaking them down into carbon dioxide and water. The universe likes this. It also happens to release heat. So both of those things will cause this process to drive forward. This is what's happening right now as you watch this video. This is happening right now as I'm speaking into this video. Your body is breaking down glucose with oxygen and making carbon dioxide and water. The universe is perfectly fine with that happening. Now, the reverse reaction is a little bit different because you're now decreasing entropy. I apologize if there's just an announcement on the loudspeaker. You're decreasing entropy. These have high entropy. This has low entropy. This has some entropy, but still the overall entropy on the right side is less than on the left side. Gases have a higher entropy than solids. They have higher disorder than solids. And more gas molecules have higher energy than fewer gas molecules. So the entropy here in this system would decline. Heat is also absorbed. Heat needs to go in. Energy needs to go into these in order to make glucose and oxygen. So the process is not favored by the universe. You do not see carbon dioxide and water spontaneously jumping together into glucose and oxygen. Now, with quantum fluctuations at some point, would it be possible for this to happen? Yes, but it's definitely not very likely. This would contradict the second law of thermodynamics, and this generally would not happen in a non-living system. The only reason why this reaction is possible is because plants over several billion years have crafted this process of photosynthesis to take these low energy molecules, incorporate light from the sun, and make a high energy molecule with oxygen. That's the endothermic process. It also decreases entropies. This has high energy in its bonds, very low entropy because it's a solid, and we are also producing oxygen in that case. Now, this process is only fueled because we have a massive energy input from the sun. The sun itself is 99.8% of the matter in our solar system, not in our universe, in our solar system. Our Earth is a teeny tiny little blip going around it. The entropy, overall entropy of the solar system is increasing. The sun is increasing in entropy as it fuses hydrogen into helium and releases heat and light. That whole system is increasing entropy over time. It's also releasing heat. And therefore, because this enormous star in the middle of our solar system is radiating all of this heat, it allows for the photosynthetic reaction, the reaction of photosynthesis, to occur only because of that massive energy input. The overall system of our universe is moving towards increasing entropy over time. Now, I wanted to take a little bit of a closer look at disorder, especially with an endothermic process. So, as I said, we can treat entropy as a form of energy. It's not the same as delta H. So, if I have salt, we know, I hope, that if we dissolve salt in water, then salt will actually absorb heat. The process should not proceed because, in general, the universe doesn't like when reactants absorb heat and become products with a higher energy value. But we're increasing entropy in this case. There's a lot more entropy here. When we dissolve salt in water, yes, it absorbs heat, but it also increases entropy quite a bit. So let's take a little closer look at spontaneous and non-spontaneous reactions. If my delta G, my Gibbs free energy, which combines heat and entropy, if that has an overall negative value, I will have a spontaneous reaction, which means overall energy is lost in the reaction or released in the reaction. Non-spontaneous reactions would be absorbing free energy from the system. So delta G is an overall free energy of any reaction. Delta H is the heat release, T is temperature in Kelvin, and delta S is entropy. And we know as temperature increases, entropy also increases. Spontaneous reactions occur when free energy is released. Non-spontaneous reactions absorb free energy, so delta G is positive, and they do not occur in most situations. They are non-spontaneous unless you get into an odd situation like the chloroplast of a plant cell. Temperature, as I said, this is in units. It's in Kelvin because we don't have, it's the only system that's not arbitrary, the only temperature measuring system that's not arbitrary is Kelvin, because it goes down to absolute zero. And when temperature goes down to absolute zero, disorder goes down to absolute zero, everything goes down to absolute zero. If I had a completely arbitrary 0 degrees Celsius, well, then I'm completely messing up my calculation, because that's a completely arbitrary value that Celsius decided should be 0 degrees, the freezing point of water. Looking at a couple of examples. Now, this is much more AP type stuff. This is Chemistry Olympiad type stuff. This is Chemistry SAT2 type stuff. Regular first year accelerated chemistry, you do not need to worry about making these calculations, but I wanted you to see how they work. So as I told you, so salt, sodium chloride as a solid, will dissolve in water, even though it absorbs energy. So at 25 degrees Celsius, which is 298 degrees Kelvin, I have a certain value for the disorder of the system if it is to dissolve. This is the entropy of aqueous sodium chloride. So when this reaction proceeds, it's absorbing 3.9 kilojoules, but I'm subtracting, and again, I just plugged in my T value, I plugged in my delta S value. Be aware, what did I do? I changed joules to kilojoules because I needed to have consistency with units. I could either make this 3,900 joules or I make this 0.07233 kilojoules. Either way, I must have consistent units. Now, this is also done per mole. So if I had 1 mole of salt, I would absorb 3.9 kilojoules and I would release 0.07233 kilojoules of energy. Now, would this process reaction proceed? It would be 3.9 kilojoules minus 21 kilojoules when I do the math. So my overall delta G is 17.6 kilojoules for each mole of salt that dissolves, which means overall energy is released. The energy is in the form of entropy, but it is released at room temperature, which is why salt dissolves in water. The universe allows that to happen because the overall energy is balancing the heat energy that is absorbed by the entropy which the universe likes, and the universe allows this reaction to proceed. This is a spontaneous reaction. As we all know, salt dissolves in water. Another example would be iron 3 oxide becoming iron and oxygen. Now this is for 1 mole of iron 3 oxide. This is rust. This is iron, this is pure iron, this is oxygen gas. If you look, these actually have a higher entropy. But this would be a very endothermic reaction because when iron reacts with oxygen, it releases a lot of heat. So at our standard temperatures and pressures, this is an endothermic reaction. The reverse is very exothermic. You take iron and you combine it with oxygen, it releases a lot of energy, a lot of heat. However, if you take iron 3 oxide and you try to change it into its constituent elements, it's going to absorb a lot of heat. So my delta H is very high. If I put my temperature at Kelvin, if I see if this reaction proceed, will iron 3 oxide become iron and oxygen at room temperature? My entropy of the overall reaction, which is the products minus reactants, you see that delta S is a positive value. So this side has greater entropy because this is a positive value. If this reaction were to proceed, we would increase entropy. We would decrease heat quite a bit. Plug in my components, so this would be 824 kilojoules minus my temperature at room temperature, and then again I change my joules to kilojoules per degree Kelvin. What do I end up finding? I find out that delta G is a positive value. The reaction is not spontaneous. However, if I raise the temperature of this particular reaction, there will be a crossing point where delta G will become, I increase my temperature, my entropy increases, it will eventually balance out my delta H. There's a point where this will become less and less positive, and it will hit 0, and then it will become negative. So when my delta G becomes 0, that's my tipping point for this becoming a spontaneous reaction. What I need to do is raise the temperature in order to make that happen. So I plug my numbers back in. I don't know the value. I don't know the breaking point at which I would go from a positive value, a non-spontaneous, to a negative value, a spontaneous. So that would set me at my target point, target temperature to make this reaction spontaneous. Delta G is 0, as I just said. I explained it already. Got to work on my animation. I do the math here. I solve for T. I find that T is 2,921 Kelvin or 2,648 degrees Celsius. Once I raise iron 3 oxide to this temperature, I end up making molten iron. I have a spontaneous reaction now. So when an asteroid, for example, an asteroid or a chunk of Mars is made of iron 3 oxide, it comes through the atmosphere, it heats up tremendously, it heats up to this temperature. Now it will become iron and oxygen because that reaction is now the favored reaction. This is why many meteorites are pure iron or have a good part of pure iron. The Egyptians would call iron celestial steel or celestial iron because it came from the sky. They didn't know how to run this process on their own to make iron, which is why the Assyrians conquered them. The Assyrians were iron makers. But this is another way. If you get iron hot enough, if you get iron 3 oxide, iron ore hot enough, you can make iron through this process. Although we also have other ways of capturing the oxygen, pulling the oxygen off of iron at lower temperatures. So this isn't necessarily the only way to make iron, but it is a possible way to do so. Now, I wanted to get to one more problem about how we would calculate delta G. In this particular case, I have energies, heats of formation. Okay, so I didn't discuss this a tremendous amount. When you take elements and you put them together, they will generally release heat. So taking hydrogen and combining it with nitrogen, you will make ammonia. That is an exothermic reaction. These elements are happier combining. That's why they do. They release energy while they do it. And they also will, actually in this case, they will increase in entropy a tiny bit, although the entropy of nitrogen is fairly close to the entropy of ammonia. But these are the components you'd be given in a table, and I actually got this from the chemistry Olympiad exam. So this was the question: what is the standard Gibbs free energy of formation? So I'm taking hydrogen and nitrogen, 3 moles of hydrogen, 2 moles of nitrogen, putting it together to form ammonia. Is this a spontaneous process? Well, my Gibbs free energy would tell me. So I have to plug in these values, keeping in mind that all of these are per mole. These values are per mole. I have 1 mole of nitrogen, 3 moles of hydrogen, 2 moles of ammonia. So what do I do for my delta H? I have to multiply it by 2 because I have 2 moles of ammonia. And then I would have my entropy of hydrogen would have to be multiplied by 3. My entropy of ammonia would have to be multiplied by 2. My entropy of nitrogen I would have as 192 joules per mole per degree Kelvin. Now I plug these values into my handy-dandy equation after I have accommodated for the doubling or the tripling depending on mole values from my original equation. Now I plug in my values. My delta S, my overall entropy, would decrease in going from 4 moles of gas to 2 moles of gas. So 3 moles of hydrogen and 1 mole of nitrogen will have more entropy than 2 moles of ammonia because we've decreased the number of particles that would be bouncing around in a system. 4 moles of gas has more entropy than 2 moles of gas. So we would actually decrease entropy by going from nitrogen and hydrogen to ammonia. However, when I plug this into my Gibbs free energy calculation, I have my joules now turned to kilojoules. I have my kilojoules of energy. This is an exothermic reaction. At room temperature, will the loss in entropy be overwhelmed by the loss of heat, which the universe likes? Things like to go from high energy to low energy. Turns out that my overall free energy loss is a negative value, which means this reaction is a spontaneous reaction in the grand scheme of things. My delta G, which I calculated for 2 moles of ammonia. That's my delta G for 2 moles of ammonia. Looking back at my reaction, if you don't understand this last part, I calculated delta G for the reaction of forming 2 moles of ammonia. That's why I plugged in all of my other values. I ended up having a negative decrease in entropy, but I have an overall increase in free energy. This calculation was based on 2 moles of ammonia. So if I'm asked to find the delta G of 1 mole of ammonia, I would divide it by 2, and that would be my negative 16.3 kilojoules of energy. That is a spontaneous reaction at room temperature. And with that, we are finished with Gibbs free energy. That was a chemistry Olympiad problem. If you're ready for something like that, again, it's just keeping track of all of the components and making sure I'm using the right values for moles, and then plugging them into delta G equals delta H minus T delta S. If you remember that, you're fine. You would have to be given delta H, you have to be given the delta S values. You plug it into the equation, take temperature, turn it into Kelvin, and you can get your answer. All right, thank you.